You can see it with the naked eye. The Milky Way's closest large galactic neighbour, and so, deep down, we imagined we could one day reach it. It seemed logical. But we were utterly wrong. If you were to travel to Andromeda using our fastest spacecraft, the Parker Solar Probe, the journey would take a full 4 billion years. This is a period of time longer than the age of the Earth itself. Because the distance between us is an incomprehensible 2.5 million light years. Even light itself can only cross this void in 2.5 million years. But the most shocking thing is not these numbers. The real shock is how the word neighbour could transform into such a massive lie. If you too want to pull back the curtain on this cosmic illusion, then like this video and subscribe to the channel. Because all your assumptions about the universe are about to be shattered. Are you ready? Let's begin. For centuries, we thought the universe was the Milky Way. Every star, every nebula, every glimmer in the sky was part of one colossal system. Beyond its borders, there was only infinite emptiness and darkness. This was a universe we knew, a universe we could measure, a comfortable universe. But a faint smudge in the sky, resting just below the constellation Cassiopeia, had been screaming this comfortable lie in our faces for thousands of years. And when we finally noticed that smudge, everything we knew changed. Because that smudge was Andromeda. It all begins with an illusion. On a clear night, if you can escape the city lights enough, you can see it. A small, silvery wisp of light, like a fingerprint left on a pane of glass. Most people don't even notice it. Because it's not a cloud, it's not a star cluster, it is an entire galaxy, the most distant object you can see with the naked eye. This fact alone challenges the human mind. But what's truly astonishing is how long it has been right in front of our eyes. The Persian astronomer al-Rahman al-Sufi described it in his book of fixed stars in the year 965 as a small cloud. He had no idea what he was seeing. Nobody did. For almost 1,000 years, Andromeda was catalogued as a gas stain within our own Milky Way galaxy. The French comet hunter Charles Messier listed it as M31, meaning the 31st object to avoid while searching for comets, an obstacle, a distraction. It was impossible for Messier to know that what he saw as a nuisance was the very key that would fundamentally change our understanding of the universe. And so, the debates began. In the early 20th century, astronomers were divided. Was the universe just the Milky Way, or were there other galaxies like it? This question peaked on April 26, 1920, in an event known as the Great Debate. On one side was Harlow Shapley, who argued that the Milky Way was much larger than previously thought, and that spiral nebulae like Andromeda were small gas clouds located within it. On the other side was Heber Curtis, who claimed these nebulae were actually island universes, meaning they were each galaxies in their own right, separated from us by incomprehensible distances. Curtis had evidence, but none of it was definitive. He had noticed that the novae in Andromeda were much fainter than those elsewhere in the sky. This suggested that Andromeda had to be extraordinarily far away. But this was just a clue, not proof. If Shapley was right, the universe was singular and understandable. But if Curtis was right, the universe was a wild infinity of trillions of galaxies. It was at this point that Edwin Hubble changed everything. In 1925, using what was then the world's most powerful telescope, the 100-inch Hooker telescope at the Mount Wilson Observatory, he identified individual stars within Andromeda. But these were not ordinary stars. They were Cepheid variables. These stars have a special rhythm. Their brightness changes in predictable cycles. And Henrietta Leavitt had shown years before that the period of this cycle is directly linked to a star's true luminosity. So, by measuring how fast a Cepheid pulsates, you can know how bright it truly is. If you compare that true brightness to how dim it appears from Earth, you can calculate the distance. Hubble measured the Cepheids of Andromeda. The result was impossible. Andromeda was not inside the Milky Way. It was far, far outside. A separate island of stars floating in the void, a approximately 2.5 million light-years away. This discovery didn't just expand the map of the universe, it permanently redefined humanity's relationship with scale. The universe went from one galaxy to at least two, then to millions, and today to an estimated 2 trillion. Every step of that expansion began with Andromeda because it is the most important galaxy for us. It is the laboratory that holds up a mirror to us, the one we can study most closely after our own. We will never have the chance to look at the Milky Way from the outside because we are trapped inside it. But we can look at Andromeda, and what we see when we look is breathtaking. It's a barred spiral galaxy similar in structure to the Milky Way, about 200,000 light-years across. It contains approximately 1 trillion stars. That is at least 2.5 times the number of stars in our own galaxy. Among those 1 trillion stars, there are millions of stellar nurseries, countless planetary systems, and at its center, a supermassive black hole with a mass of 100 to 200 million times that of the Sun. Andromeda is not just a galaxy, it is a titan. It is the largest member of the local group, a collection of about 100 galaxies that includes both the Milky Way and Andromeda. And yet, despite all this overwhelming size, there is a word we use, a definition we constantly repeat: neighbor. Andromeda is our closest large galactic neighbor. But this word conceals a truth that will blow your mind. The word neighbor implies proximity in the human brain, accessibility, a surmountable distance. But when it comes to Andromeda, this intuition is the biggest lie upon which this story is built, and so everything hinges on that one crushing number. 2.5 million light-years. It sounds almost manageable, just 2.5 million. But light-years are not ordinary kilometers. A single light-year is the distance light travels in 1 year at a speed of 300,000 kilometers per second. That's about 9.5 trillion kilometers. Now, multiply that number by 2.5 million. This is a weapon that destroys intuition. But have you ever tried to truly feel what this number means? To fully grasp the terror of this distance? We must first start somewhere much smaller. We must start in our own home. We must start with the solar system and understand just how small it is. Because the solar system, with its giant planets and billion-kilometer orbits, is actually less significant than a speck of dust. Let's start with the Moon, the closest celestial body to us. It takes light only 1.3 seconds to travel this distance. The Apollo astronauts got there in 3 days. This is a distance humanity has physically crossed. It's manageable. But our distance to the Sun is about 150 million kilometers. It takes light 8 minutes and 20 seconds to cross this distance. We've never been there. The fastest object humanity has ever made, the Parker Solar Probe, has come within 6.1 million kilometers of its surface. This probe, during its closest approach, reached a speed of 700,000 kilometers per hour. Keep that number in mind, we'll need it later. But this is just our own backyard. The Oort cloud, which marks the gravitational boundary of the solar system, extends over an area about 1.6 light-years wide, nearly 15 trillion kilometers. Voyager 1, launched in 1977 and the most distant object humanity has ever sent, has been traveling for about 50 years at a speed of 61,000 kilometers per hour. And in those 50 years, it has covered just a little more than 1,000th of the distance to the outer edge of the Oort cloud. Our most ambitious explorer, after a half-century journey, has not even reached the fence of our own backyard. And so, we now step onto the first rung of the ladder, outside our own star system. We are stepping out onto the cosmic street, and this street is interstellar space. The closest star system to our Sun is Alpha Centauri. It's actually a triple system. But the closest single star to us is Proxima Centauri, about 4.24 light-years away. This is the shortest meaningful step beyond our own system, and it is already a number that should make a person uneasy, because 4.24 light-years means that it takes even light 4 years and 3 months to cross this void. This is not an engineering problem. This is the most fundamental law of physics, the universal speed limit. There is no known technology, no signal, no spacecraft that can cover this distance in less time. What about a man-made craft? If Voyager 1 were headed towards Alpha Centauri, the journey would take about 73,000 years. All of recorded human history, about 5,000 years, is just a small fraction of this time. Voyager 1 would need a period 14 times the length of our entire civilization's history to reach the nearest star. And what about our fastest craft? The Parker Solar Probe? Even at its incredible speed, the journey to Alpha Centauri would take about 6,600 years. This is like going back to an era when writing had not yet been invented, and the first cities were still thousands of years away. But this is just the first step, just the nearest neighbor. The ladder goes much, much higher. Because Gassant, our entire galaxy, the Milky Way, is about 100,000 light-years across its visible disk. This means it takes light itself 100,000 years to go from one end to the other. If you were standing on one side of the galaxy and shone a laser to the other, there would be a time gap of 100,000 years between you and any being who received your signal. Any reply they sent would take another 100,000 years to reach you. A single round-trip conversation, 200,000 years. The entire history of the Homo sapien species fits comfortably within this gap. Our galaxy contains 200 to 400 billion stars. These stars are not crowded. The average distance between stars in our region, like that between the Sun and Alpha Centauri, is about 4 to 5 light-years. The galaxy is enormous. But it is mostly empty space. In fact, everything you know, every planet you've seen, every mission we've launched, every distance covered by a man-made object, exists in such a tiny area compared to our galaxy that it mathematically rounds to zero. And now we come to that critical moment, that turning point, because everything described so far, every distance, every impossible number, is located within our own galaxy. The nearest star, the galactic disk, the 100,000 light-year crossing, it's all local, it's all inside our home. But Andromeda is not inside our home. Andromeda is about 2.5 million light-years away. The Milky Way is about 100,000 light-years wide. This means the distance to Andromeda is 25 times the entire diameter of our own galaxy. Imagine standing at one end of a football field. The opposite goal line represents the other end of the Milky Way, 100,000 light-years away. Now, on this scale, how far away would Andromeda be? The answer is 25 football fields away. 25 full fields, each representing the width of a galaxy containing hundreds of billions of stars. You could line up 25 galaxies the size of the Milky Way end to end in the space that separates us from Andromeda, and there would still be room left. This is the moment when interstellar distances, the voids within a single galaxy, are themselves dwarfed by intergalactic distances by the same savage ratio. It's like leaving a house and stepping into a city. Then it's like crossing a continent. But going to Andromeda is like crossing the ocean. An ocean so vast that the entire continent you just crossed is not even visible from the opposite shore. Thus, sir, we now see the true meaning of that misleading word, closest. When astronomers say Andromeda is our closest large galactic neighbour, they are telling the truth, because the next closest major galaxies are about 12 to 14 million light-years away. Andromeda is indeed the next-door neighbour. But closest does not mean close. It does not mean reachable. It just means that everything else is even worse. Andromeda is the least impossible distant major galaxy. We have climbed this conceptual ladder. We have seen the light seconds to the moon, the light minutes to the sun, the terrifying years to the nearest star, and the mind-boggling millennia of our galaxy. All of this was to prepare us for one overwhelming truth. The scale of the universe outside our galaxy is a completely different beast. We now understand these concepts. But what do these numbers and theories actually point to? What do the observations say? When we look at that pale smudge of light, what do we actually see beyond this terrifying distance? And now comes the real shock. Because what we see beyond that distance is even more terrifying than the distance itself. What we see defies logic. It shatters theories. and it slams into our faces just how ruthless the universe can be. Here are the findings. The first shock is that Andromeda is not just a galaxy, it is a titan, a giant hiding behind the word neighbor. Our galaxy, the Milky Way, is a big place, about 100,000 light-years across. It contains 200 to 400 billion stars. These numbers are already incomprehensible. But when we look at Andromeda, these numbers become laughable. Andromeda is about 200,000 light-years wide. It spans an area almost twice that of our galaxy, and the number of stars within it? Approximately 1 trillion. This is at least 2.5 times, and by some estimates 5 times, the number of stars in the Milky Way. Even by the most optimistic counts, 1 trillion suns, each with a potential planetary system. This should not have been. A neighbor is similar to you, maybe a little bigger, a little smaller. But this is not a neighborhood. This is a skyscraper built next to a studio apartment. Therefore, the phrase closest large galaxy is a lie. Because Andromeda is not just large, it is the overwhelming ruler of our region, a gravitational monster that makes all other galaxies in the local group, including the Milky Way, look like dwarves. This fact transforms Andromeda from a peer into an anomaly. But the real anomaly is hidden at its center. Every large galaxy has a supermassive black hole at its core, the black hole at the center of our Milky Way, Sagittarius. A star has a mass of about 4 million times that of the Sun. This is already a huge number. But when we look at the center of Andromeda, what we see is impossible. The black hole at Andromeda's core has a mass of 100 to 200 million times that of the Sun. This means it is 25 to 50 times larger than our black hole. When two galaxies are roughly similar in size, there shouldn't be such a huge difference between the monsters at their centers. This is a situation that is completely out of proportion. This shows that Andromeda's past was much more violent, much more bloody than ours. That black hole must have grown by swallowing countless stars and even smaller galaxies over billions of years. If the black hole at our center is a piranha, Andromeda's is a megalodon. Therefore, the relationship between the two galaxies is less like a neighborhood and more like a predator and prey relationship. Right next to our seemingly calm galaxy stands the home of a much more feral and insatiable beast, and we have only known this truth for the last few decades. But the cruelty of the universe does not end here. Perhaps the most vicious shock came from the Hubble Space Telescope. In January 2015, Hubble completed the largest photographic mosaic in its history, a panoramic image of Andromeda's disk. This project was created by combining over 600 photographs taken over more than a decade, using over 1,000 Hubble orbits. The result? A 2 billion pixel image. But that's just a number. The real shock is what is visible in that image. The image allowed us to resolve over 200 million individual stars in a galaxy 2.5 million light-years away. Stop and think about that. 200 million separate points of light, each one a sun. We can count them one by one. This should not have been possible from that distance. It's like trying to count grains of sand on a beach across the ocean from the top of a mountain. Hubble did it. But this is not a victory. This is a torture. Because this photograph transformed Andromeda from an abstract smudge into a tangible, real place full of stars. Now we know. There are star clusters there. There are dust lanes. There are millions of worlds. The universe has given us a map of paradise, but it has closed all the roads to get there. It has shown us everything, but forbidden us to touch. And the final blow comes from the simplest observation, with the naked eye. The area Andromeda covers in the sky is about 6 times the apparent diameter of the full moon. I repeat, 6 times the size of a full moon. If our eyes were sensitive enough to perceive all its faint light, it would stretch across the sky as a huge as long glow. This is an assault on all our intuitions. How can an object 2.5 million light-years away occupy such a large space in our sky? This completely destroys our brain's perception of distance and size. This is not an optical illusion. This is pure geometry. But this geometry contradicts our instincts. We think that what we see must be close, that what looks big must be even closer. Andromeda both appears enormous and is unimaginably far away. This is a contradiction, a paradox, and this paradox is the foundation of the unease we feel when we stand in the darkness of night and look at that pale smudge. Our eyes are telling us one thing, the laws of physics are telling us the exact opposite. Therefore, looking at Andromeda is not just looking at a distant object. It is confronting the limits of our own perception and how the universe deceives us. On one hand, there is a Titan galaxy that crushes us. It harbours a disproportionate monster at its centre. We can take an incredibly detailed photograph of it, and it appears deceptively large in our sky. But how do all these proofs, all this tangible reality, merge with that one brutal truth? 2.5 million light-years. Doesn't this flood of information, this feeling of closeness, only make the walls of the prison created by that distance even thicker? Isn't every new detail we see just another iron bar, reminding us of how helpless we truly are? Is the universe offering us a gift by showing us Andromeda? Or is it just mocking us? Because the most ruthless proof of this mockery is hidden in the message that comes from the distance itself. This message is older than time itself. Because every single photon, every particle of light that falls on your retina tonight from Andromeda began its journey 2.5 million years ago. This is not a number. This is a time machine. What you're seeing now is not Andromeda as it is today. It is Andromeda as it was before a species called humanity even appeared on Earth. This light is the light of a ghost. Therefore, let's take a walk back in time. Let each of our steps represent an era that light crossed to reach you. Let's go back just 500 years. Christopher Columbus had just crossed the Atlantic. The Renaissance was reshaping Europe. The light from Andromeda still had 500 years to complete its journey. Let's go back 5,000 years. The first cities were rising in Mesopotamia. Writing was being invented. History was beginning. That light had been on its way for 2,495,000 years. Let's go back 50,000 years. Modern humans were painting in caves in Europe, making bone tools. The light's journey was 98% complete. But it still had 50,000 years to go. Let's go back 300,000 years. Our species, Homo sapiens, first appeared in the fossil record. That light had already been travelling for 2.2 million years when our species was born. And now, let's go back 2.5 million years. Homo habilis, the first human ancestor, was chipping simple stone tools in East Africa. That is the moment. The light reaching your eye tonight left Andromeda at that exact instant. The entire human lineage, from Homo habilis to Erectus, from Neanderthals to us, was born, lived, and vanished within the travel time of this light. The light you see is older than our species, older than our genus. This should not be. Physical reality should not feel this fractured. But now comes the true paradox. This galaxy, at this unimaginable distance, is coming towards us, and at an incredible speed. The blue shift, first measured by Vesto Slipher in 1912, shows that Andromeda is closing the distance at a speed of about 110 kilometers per second. That is about 400,000 kilometers per hour. At this speed, you could go from New York to Tokyo in less than a minute. This is faster than even the fastest man-made vehicles. So, you might think this enormous gap is closing quickly. But you cannot, because when this speed is applied to a distance of 2.5 million light-years, the resulting timeline is billions of years. The Milky Way and Andromeda were supposed to collide and merge in about 4.5 billion years. This was a fact that science had accepted as certain for decades. But recent discoveries have shaken even this truth. The most current simulations using Gaia and Hubble data show that this collision is not certain. The gravitational influence of the Large Magellanic Cloud, orbiting the Milky Way, could be deflecting our galaxy's path, and the two giants might just graze past each other. Some models now reduce the probability of a merger to as low as 50%. Can you imagine? Two galaxies approaching each other at 110 kilometers per second. And whether they will collide or not is still a coin toss. Because the space in between is not just large, it is also empty. Unimaginably empty. The interstellar space within our galaxy contains about 1 atom per cubic centimeter. This is already incredibly sparse. But the intergalactic space, that chasm between us and Andromeda, contains 1 to 10 atoms per cubic meter. A cubic meter, not a cubic centimeter. This means it is 1,000,000 times emptier than the space between stars. The best vacuum chambers we can create in a lab on Earth are millions of times denser than this void. This is the kind of emptiness that makes a journey impossible. Because this is a void with nothing in it. There are no stars to get a gravitational assist from. There are no gas clouds to refuel. There is nothing to navigate by. Just an absolute nothingness stretching for 2.5 million light years. The Milky Way as a faint smudge in one direction, and Andromeda as a faint smudge in the other. And between them, for 1,000,000 light years around you, the universe is functionally empty. This is where the word journey loses its meaning. This is not a journey. This is a fall into nothingness itself. So, we have a series of impossible facts, a light older than our species, a neighbour approaching at 400,000 kilometers per hour but billions of years away, and between them, a void emptier than anything humanity has ever created. Each of these discoveries, on its own, challenges our understanding of the universe. But, when they all come together, the picture becomes even more disturbing. This is not just a story of big numbers. This is a story that shows how scale is a property that can make even the most fundamental laws of physics seem meaningless. So, how does this work? How can we measure these unimaginable distances with such precision? The shocking discoveries of Part 2 are not random guesses. They are the result of ingenious yet ruthless measuring tools the universe has offered us. And when you understand these mechanisms, you see that the universe has given us tools not only to look, but also to understand. But these tools also show just how solidly our prison is built, because the physics underlying these measurements. So how does it work? How are we able to measure these incredible distances, these unbelievable speeds, with such precision? The shocking discoveries of Part 2 are not random estimates. They are the result of ingenious and yet cruel measuring devices the universe itself provides. Now, let's gently pry open the lid of that toolbox. Let's move away from the fast-paced discoveries and take a closer look at the elegant yet complex mechanisms behind these numbers. Because these mechanisms show how the most fundamental laws of the universe can be used to measure distance and time. It all begins with a standard candle. This is the most fundamental concept in cosmology. Imagine a light bulb in a dark room. If you know that bulb is a 100-watt bulb, so you can estimate how far away it is just by looking at how dim it appears. If it's very dim, it's far away. If it's bright, it's close. Well, Cepheid variables are the 100-watt light bulbs the universe has given us. These are massive, young stars that periodically expand and contract, and in doing so, their brightness increases and decreases. The person who unlocked their secret was an astronomer named Henrietta Leavitt in 1912. Leavitt discovered a direct relationship between a Cepheid's pulsation period and its true brightness. The longer the period, the greater the star's intrinsic luminosity. This was a revolution in cosmology. Because we now had a standard candle, measuring a Cepheid's period, which can range from a few days to more than 50 days, meant knowing how bright it truly is. All that remained was to compare that true brightness with its apparent dimness from Earth. The difference was a measure of distance. This is exactly what Edwin Hubble did with his 100-inch telescope. He measured the pulsations of the Cepheids in Andromeda, calculated their periods, and found their true brightness. This brightness proved they were far too dim to be inside our galaxy. His initial calculations put the distance at about 900,000 light-years, because it was not known at the time that there were two different types of Cepheids. But even this first number changed the universe forever. This method is so effective because it turns a simple physical relationship into a universal ruler that measures unimaginable distances. But Cepheids are not the only tool. In fact, they are not perfect. Because Cepheids are young, massive stars, therefore, they are often found in the dusty, star-forming regions of galaxies. This dust can block their light and lead to errors in distance measurements. That is why astronomers needed another standard candle, a more reliable and cleaner measuring tool, and they found it in the death throes of old stars. This method is called the tip of the red giant branch, or TRGB for short. You can think of it as a fuse that always blows at the same brightness. When a low-mass star reaches the end of its life, it becomes a red giant. In this process, its core, made of helium, gets hotter and denser. When the core temperature reaches about 100 million Kelvin, helium fusion begins suddenly and explosively. This is called the helium flash. This critical moment is the key to the TRGB method, because this helium flash always occurs at almost exactly the same absolute luminosity. The star's absolute magnitude in the infrared I band reaches a peak at m_I approximately equals -4.05. This is a universal threshold that applies to similar stars everywhere in the universe. So, when you find the brightest red giant stars in a galaxy and measure their brightness, you will suddenly see a cutoff. That cutoff point is the tip of the red giant branch. Since you know the brightness of that point, you now have a standard candle that is even more precise than Cepheids. This method is incredibly effective, especially for old star populations that are abundant in the dust-free outer halos of galaxies. The TRGB measurements for Andromeda have determined the distance to be 2.56 million light-years. And this is one of the most reliable measurements that form the basis of modern estimates. So, we have two powerful methods for measuring distance. One uses young, pulsating stars, the other uses dying, old stars. But another shocking fact about Andromeda, the fact that it is approaching us was revealed by a completely different mechanism. This mechanism measures not distance, but velocity. And it does this by analysing the colour of light. This is a phenomenon known as the Doppler effect. You're familiar with it from daily life. The siren of an ambulance approaching you makes a high-pitched sound. Because the sound waves are compressed. As it moves away from you, its sound becomes lower-pitched. Because the sound waves are stretched. Light is also a wave and behaves in exactly the same way. If an object is moving towards you, the light waves it emits are compressed and shift towards the blue end of the spectrum. This is called blue shift. If the object is moving away from you, the light waves are stretched and shift towards the red end of the spectrum. This is called redshift. In 1912, Vesto Slipher passed Andromeda's light through a prism and analysed its spectrum. What he saw was revolutionary. The characteristic lines in Andromeda's spectrum were not where they were supposed to be. They had shifted towards the blue. This was the first evidence that Andromeda was coming towards us. Slipher's initial measurements calculated the speed at about 300 kilometers per second. Later, more precise measurements corrected this speed to about 110 kilometers per second relative to the Milky Way. This method does not tell us the distance to Andromeda. But it gives us much more dynamic information. It shows that the relationship between us is not static, but a gravitational dance changing over a timescale of billions of years. The blue shift transformed Andromeda from a passive smudge in the sky into a moving entity that will play an active role in our future. These three mechanisms, Cepheids, TRGB, and blue shift, are the building blocks of our basic knowledge about Andromeda. One uses the rhythm of pulsating stars, another the last gasp of dying stars, and the third the colour-shifting whisper of light to paint a portrait of a galaxy. Each method confirms the others and adds a new layer to the picture. One tells us how far away it is, another confirms that measurement, and the third reveals which way it's going. This is a perfect example of how science self-corrects and builds a more holistic picture by bringing together different lines of evidence. But these are just the most well-known tools. The toolbox is much deeper. There are other, more subtle methods. For example, systems like eclipsing binary stars, which orbit each other and periodically eclipse one another. The timing and brightness changes of these eclipses provide incredibly precise data on the physical properties of the stars and therefore their distances. And the details of this synchronization, how these different measurements come together to build a single, solid reality, is truly awe-inspiring. And this synchronization reaches its peak with even more precise methods like eclipsing binaries. Because this method relies not just on brightness, but on fundamental physics itself, gravity and orbital mechanics. Think of it like two perfectly synchronized dancers. They orbit each other so precisely that they periodically pass in front of each other from our point of view. During these transits, we observe tiny dips in the system's total brightness. These dips are a treasure map. How deep these dips are, how long they last, and how often they repeat gives us incredibly precise information about the star's sizes, masses, and orbital velocities. Using this information, we can calculate the true brightness of the stars almost flawlessly. This is more than a standard candle. This is a measuring device calibrated by the universe itself. For example, in a 2005 study, the distance was measured as 2.52 million light-years using an eclipsing binary system in Andromeda. The margin of error for this measurement was only about 2%. While the Cepheid and TRGB methods rely on the statistical properties of star populations, this method relies on the fundamental physical properties of a single system. Therefore, it is an invaluable reference point for checking and calibrating the results of other methods. This method is so effective because it eliminates speculation. It is less dependent on assumptions about how stars evolve or what their atmospheres are like. It relies only on the laws of Newton and Kepler that we have known for hundreds of years. This is science in its purest form. Simple observation and basic physics come together to measure an unimaginable distance. But what if you're too far away to see a galaxy's individual stars? Then you need to resort to a completely different mechanism, a statistical trick. This is called surface brightness fluctuations, or SBF. Imagine looking at a cornfield from a distance. From very far away, the field looks like a single green color. But as you get closer, you notice a bumpy texture created by individual corn plants. Some spots look brighter, some darker. The SBF method does exactly this, but with stars instead of corn plants. When you take an image of a distant galaxy with a telescope, each pixel contains the combined light of thousands of stars. If the galaxy is close, each pixel contains fewer stars. Therefore, the brightness differences between pixels, the fluctuations, are more pronounced. The image looks bumpy or mottled, but if the galaxy is far away, more stars fit into each pixel. This creates a statistical averaging effect, and the brightness differences between pixels decrease. The image looks smoother. By measuring the amount of these fluctuations, you can determine how far away the galaxy is with incredible precision. This method is especially valuable for elliptical galaxies, where it is impossible to resolve individual stars. Infrared SBF measurements for Andromeda have given the distance as 2.57 million light-years. This is in startling agreement with all other methods. The beauty of this technique is that it eliminates the dependence on standard candles. It relies only on the statistical properties of star populations and the resolution of the telescope. This is a completely independent rung on the cosmic distance ladder. Therefore, we have a set of independent and mutually verifying methods. The rhythm of Cepheids, the final glow of TRGB, the dance of eclipsing binaries, and the statistical roughness of SBF. When they all come together, they paint an extremely consistent picture of Andromeda's distance: 2.51 million light-years, 2.56 million light-years, 2.52 million light-years, 2.57 million light-years. These numbers are all very close to each other. The small differences between them stem from each method's own calibration challenges and observational uncertainties. But these small differences should not overshadow the main story. The main story is that 4 different methods, based on completely different physical principles, arrive at almost the same result when measuring one of the greatest distances in the universe. When scientists combine all this data, the most current scientific consensus for Andromeda's distance is determined to be about 2.54 million light-years, and the margin of error for this number, plus or minus 110,000 light-years, is less than 4% of the distance itself. This is a triumph of human intellect and the scientific method. We can measure the distance of an object recorded as a faint smudge in the sky thousands of years ago with a precision of a few percent. But this victory is also a tragedy. Because Cepheid is neen, this certainty shows there is no escape. This number is not a guess. It is not a speculation. It is a proven, verified, cross-checked fact that the universe is telling us in multiple languages. All these methods were designed to measure that unimaginable distance. They gave us the answer to the question, how far? But there is also a how fast dimension to this story. And that speed makes everything even more complex and even more terrifying, because Andromeda's speed of 110 kilometers per second towards us is only part of the picture. The movements of galaxies are not just a simple fall towards each other. They are the result of the complex orbits of the Milky Way and Andromeda within the local group. And modeling these orbits gives us the ability to predict what will happen billions of years from now. These models must account not only for the laws of gravity, but also for the invisible effect of dark matter, the gravitational interventions of other small galaxies, and even the expansion of the universe itself. The latest models are examining how a large satellite galaxy like the Large Magellanic Cloud affects the Milky Way's orbit and how this could change our rendezvous with Andromeda. These simulations create hundreds of thousands of virtual universes, changing small initial conditions in each one to see which outcomes are most likely. A study published in 2025, using over 100,000 simulations, found the probability of a merger was only 50%. But, a year later, another study with newer data raised this probability back to 90%. This shows that science is a living process. The answers can change. But the underlying physics remains the same, and that physics says that two giants have an inevitable gravitational rendezvous. But the exact timing and outcome of that rendezvous depend on a complex dance of small effects accumulated over billions of years. All these mechanisms tell us one thing: the universe has rules, and when we understand these rules, we can do incredible things. But what's truly exciting is where these rules lead us. Because when we understand these numbers and mechanisms, we're no longer just looking at a distance, we're looking at a timeline, we're looking at a future. And that future holds the darkest and most violent climax of this story, because the timing of these journeys, these billion-year calculations. But what's truly exciting is where these rules lead us. Because when we understand these numbers and mechanisms, we're no longer just looking at a distance, we're looking at a timeline, we're looking at a future. And that future holds the darkest and most violent climax of this story, because now we will translate that distance into human time. We will turn them from numbers into heartbeats, into generations, into the lifespans of species. The calm, methodical pace of part 3 is over. Now we reach the climax. Buckle up. Because what you're about to see will hit you like a slap in the face, showing just how thick the walls of a prison are, how insurmountable, and in what a tiny room we actually live. Numbers lose their power when they get too big. 2.5 million light years. It's an abstraction. So, let's translate it into time, because everyone understands time. Let's start with the fastest object humanity has ever made, the Parker Solar Probe. The record speed it reached during its solar flyby in December 2024, about 700,000 kilometers per hour. That's more than 120 kilometers per second. At this speed, you could circle the Earth in less than 3.5 minutes. You would reach the Moon in 33 minutes. This is the pinnacle of our species' ability to make something move fast. Now let's point it at Andromeda, 2.5 million light years, 14.7 quintillion kilometers. At this speed, it would take the Parker Solar Probe about 3.9 billion years to reach the Andromeda galaxy. Let's round it. 4 billion years, 4 billion years. This number is so large our brain rejects it. But this is a record. The record for the time it takes humanity's fastest vehicle to reach its closest neighbor. And this record is a monument to shame. Because the Earth itself is about 4.5 billion years old. This means if a Parker probe had been launched the moment our planet solidified from its primordial molten rock disk, that probe would still not have reached Andromeda today. It would still be on its way. It would have about 500 million years of travel left. Our entire geological history, every mass extinction, every ice age, every tectonic upheaval, every evolutionary epoch that produced fish, dinosaurs, mammals, and eventually a species capable of building that probe, would have passed during this journey, and the probe would still not have reached its destination. This is not a journey. This is a geological process. But that's not enough. Let's increase the speed. Let's push past the limits of engineering and into the realm of theoretical physics. Let's assume we build a spacecraft that reaches 1% of the speed of light. That's about 10.8 million kilometers per hour, 15 times faster than the Parker probe. This is one of the most extreme speeds theoretically possible with concepts like nuclear pulse propulsion. Here it is, the fastest hypothetical ship in history. But Elst, even this ship is helpless, because cars at 1% of the speed of light, the journey to Andromeda would take 250 million years, 250 million years. Do you know what this amount of time means? It's close to a galactic year, the time it takes for our solar system to make one full orbit around the galactic center. When the probe was launched, the dinosaurs had not yet gone extinct. Mammals were small, timid creatures hiding from predators. The continents were arranged in configurations unrecognizable on a modern map. By the time the probe arrived, the Earth itself might be unrecognizable. It might have been reshaped by millions of years of geological and biological evolution. The civilization that launched the probe would be separated from its arrival by a time chasm wider than the entire age of complex multicellular life on Earth. This is IM Pos Sci. This is a timescale that destroys the meaning of the word journey. We must go faster. We must shatter the limits of logic. Let's go to 10% of the speed of light, 108 million kilometers per hour. This is such an extreme speed that no serious engineering proposal has ever suggested it for a physical spacecraft. Because, at this speed, a collision with even the smallest dust grain would impart the kinetic energy of a small bomb to that grain. Your vehicle would be instantly destroyed. But, let's ignore these problems. Let's assume the engineering is solved. At 10% of the speed of light, the journey to Andromeda would take 25 million years. 25 million years. This is the amount of time that separates our present day from the late Oligocene epoch, when the ancestors of modern apes began to diverge from earlier primate lineages. The entire evolutionary journey from small tree-dwelling primates to spacefaring humans fits within the travel time to Andromeda at 10% of the speed of light. The journey is so long that there might not even be a biological continuity between the species that starts it and the species that completes it. This would be the loneliest journey in history, because when you arrived, the world you left behind would be lost not just in time, but in evolution. But all of this is in vain, because the universe has an ultimate speed limit, and even when we reach that limit, the horror only deepens. Let's travel with light itself, at 300,000 kilometers per second, the absolute maximum speed allowed by the universe. At this speed, the journey to Andromeda takes 2.5 million years, not one less, 2.5 million years. This is not a number you can put into context with human history. Because human history does not go back that far. The entirety of recorded history, that 5,000 to 6,000 year memory of civilization, fits into the duration of this light journey about 400 times. So, let's walk back in time. Let each of our steps represent an era that light crossed to reach you. 5,000 years ago, history began. The light's journey was 99.8% complete. 10,000 years ago, agriculture was invented. The Ice Age was ending. The light's journey was 99.6% complete. 300,000 years ago, our species, Homo sapiens, emerged. That light had already been traveling for 2.2 million years when our species was born. We're not even a footnote in that light's journey. And now, let's go back 2.5 million years. Homo habilis, the first member of our genus, was chipping simple stone tools in East Africa. That is the moment. The light you see tonight left Andromeda at that exact instant, as our primitive ancestors made their first tools. The light you see is older than the human genus. The entire human lineage is younger than that light. This is not a fact the mind can grasp. This is an assault on existence itself. And now comes the final and most brutal blow. Forget the journey. Get the idea of going there out of your head. What if you just wanted to communicate, to send a message and get a reply? You send a radio signal at the speed of light towards Andromeda. The signal sets off. It arrives 2.5 million years later. Let's assume there's a civilization there and they're listening. They decode your message. They write a reply. They send it back also at the speed of light. Another 2.5 million years pass. The reply reaches Earth. The total time for a single, "Hello, how are you?" and "I'm fine, how are you?" exchange. 5 million years. 5 million years ago, Our ancestors had just split from the chimpanzee lineage. They were Australopithecus, half ape, half human creatures. If a human civilization had somehow existed 5 million years ago and sent a greeting to Andromeda, the reply arriving today would reach a planet that shared no language, no culture, no memory, and not even a species identity with the senders. The civilization that sent the message would be as alien to the civilization that received the reply as an Australopithecus is to a modern astronaut. Communicating with Andromeda is not impractical. It is meaningless, because the timescale destroys the very concept of a conversation. No entity at either end can exist long enough to participate in both halves of the exchange. This is the cruelest truth of distance. It isolates you not just physically, but temporally. It turns you from a prisoner into a ghost. All these impossible journeys, these billion-year durations, these meaningless conversations, all lead to the same conclusion. Andromeda is not a place, it is a boundary. But what does this boundary mean? What does this distance, this isolation, mean for the rest of the universe? Because the most terrifying part of this story is that Andromeda is not an exception. It's not the worst-case scenario, it is the best-case scenario. And what this fact implies is darker than anything you've heard so far, because the distance to Andromeda shows us a truth about the architecture of the universe. It is not an exception. It is the rule itself. Galaxies are separated by voids spanning millions of light years. This is not a coincidence. This is how the cosmos is built. Therefore, when we look at the rest of the universe, this horror only multiplies. This is not a garden. This is an archipelago of island galaxies, and each island is separated from the next by insurmountable oceans. If this is the closest, how much worse can the others be? Now you will see just how deep those oceans are. The first record comes from the nearest major galaxy cluster, the Virgo cluster. This is a city, a crowded metropolis where thousands of galaxies are bound together by gravity. But how far is this metropolis from us? About 54 million light years. That is more than 20 times the distance to Andromeda. The time required for the Parker Solar Probe to cover this distance increases from 4 billion years to 85 billion years. This is more than 6 times the age of the universe itself. You have to spend a time traveling that is longer than the universe has existed. How can this be possible? When the light from the Virgo cluster reached Earth, the dinosaurs were long extinct, and the first primates were swinging in the trees. Each of the more than 1,300 galaxies in that cluster is an even more impossible target than Andromeda. This is the moment when the next rung on the distance ladder completely obliterates the rung below it. The discovery of the Virgo cluster shocked astronomers, because it showed that the universe is composed not just of individual galaxies, but also of these massive galaxy cities. But these cities were so far apart that the very idea of travelling between them turned from science fiction into pure fantasy. The scientific world realised that the universe was much lumpier than they had thought, and these lumps were structures with immense voids between them. But this was just the beginning. There was something even bigger. Clusters also come together to form even larger structures, superclusters. Our own local group, along with the Virgo cluster, is just a small part of a colossal structure known as the Laniakea supercluster. This is one of the largest local structures ever mapped. Laniakea means immeasurable heaven in Hawaiian, and the name does it justice. Because this structure is about 520 million light-years across, it contains over 100,000 galaxies. Its total mass is 100 quadrillion times that of the Sun. These numbers defy the human mind. This is more than 200 times the distance to Andromeda. It takes light more than 500 million years to travel from one end of this structure to the other. When this light began its journey, complex life was just beginning on Earth. How can this be possible? The discovery of Laniakea showed that the structure of the universe is much more organized and hierarchical than we thought. Galaxies form clusters, clusters form superclusters, and these superclusters are strung along the threads of a cosmic web. When this discovery was published in 2014, it sent shockwaves through the scientific community, because it even changed our definition of galaxy. The Milky Way was no longer a solitary entity, but part of this gigantic cosmic continent called Laniakea. And we were inhabitants of a remote corner of that continent. And now we go to the deepest level, to the observable universe itself, to the farthest limit our telescopes can see. This limit is determined by the distance that light has had enough time to travel to reach us since the Big Bang. And this distance is about 46.5 billion light-years in every direction. That means a sphere 93 billion light-years in diameter. This is the universe's record. We cannot see beyond it. Because the light from anything further away has not yet reached us. Within this gigantic sphere, there are an estimated 2 trillion galaxies. 2 trillion? That's 10 galaxies for every single star in the Milky Way. How can this be possible? This number emerged from estimates based on the Hubble Space Telescope's deep field images. The telescope focused for weeks on a tiny patch of sky that appeared completely empty. And in that emptiness, it found thousands of galaxies, each a smudge of light, each a world of billions of stars. And this was in an area as small as a pinhead. This discovery showed scientists just how full the universe is. But this is not a crowd. This is an illusion, because these 2 trillion galaxies are spread out over 93 billion light-years. This means the average distance between galaxies is millions of light-years. The observable universe is not a list of destinations. It is a gallery of windows. You can look through each one, but you can never enter any of them. But the darkest and most epic truth of this story is that these windows are slowly closing. Forever. Because the universe is expanding, and this expansion is accelerating. This is driven by a mysterious force called dark energy. This force is stretching space itself, pushing galaxies apart from one another. Except for small gravitationally bound groups like our local group, all other galaxies in the universe are moving away from us, and the farther away they are, the faster they recede. At a distance of about 14 billion light-years, this speed of recession exceeds the speed of light. This is not a violation of the laws of physics, because the galaxies are not moving through space. Space itself is expanding with them. This means those galaxies have now passed beyond our cosmological event horizon. No signal we send to them will ever reach them. No light from them will ever reach us. They are, for us, as if they have been erased from the universe, and this process is ongoing. Every second, more galaxies cross this irreversible boundary. Future astronomers, in about 100 billion years, will look up at the sky and see nothing but their own merged Andromeda galaxy. The rest of the universe will be lost from their observations forever. All evidence of the Big Bang, of the expansion of the universe, of the other trillions of galaxies, will be erased. This may be the greatest discovery in history, the ultimate proof of our cosmic solitude. We are living in an age when the lights of the universe are slowly going out, and Andromeda is the last great light that will remain bound to us. And we possess unimaginable knowledge of the universe. On the other, we are in a state of absolute impotence when it comes to physically accessing it. We are both an all-knowing God and a prisoner who can never leave his cell. Think about it. We have a 2 billion pixel map of Andromeda. On that map, we can count over 200 million individual stars, single suns burning like nuclear furnaces. We can measure the mass of the black hole at its center as 100 million times that of the Sun. We know that it collided with another galaxy 2 billion years ago, and that we can still see the waves of star formation created by that collision. This is an incredible triumph of the human mind. We know the history, structure, and chemistry of a place 2.5 million light-years away better than the history of most countries on our own planet. But all this knowledge only underlines a bitter truth with a thicker pen. We can never go there. We can never set foot on any of those 200 million stars. This is the myth of Tantalus, looking with eternal hunger and thirst at the fruit and water that stand right before him, but which he can never reach. The universe presents us with the most detailed menu of the banquet, but it does not seat us at the table. This knowledge is not a power, it is a torture, because every new detail we learn makes the walls of our prison more distinct and reminds us just how magnificent the view is through the bars. But here is the but moment. Perhaps this is not a prison. perhaps this is the greatest freedom the universe has offered us. Because our physical bodies may be chained to this planet, to this solar system, but our consciousness, our thoughts, our imagination can cross 2.5 million light years in seconds. The 1.5 kilogram universe of water and fat inside your brain, just as the minds of Edwin Hubble and Henrietta Leavitt did, can traverse that void. You, while reading these lines or listening to these words, can think about the supermassive black hole at the center of Andromeda. In that moment, your consciousness has instantly crossed a distance that light takes 2.5 million years to travel. This is the greatest miracle in the universe. We may not be able to travel physically, but mentally, we can journey to every corner of the universe, all the way back to the beginning of time. You're not just a being of flesh and bone. You're a tool the universe uses to understand itself, and this is a far greater journey than any starship could ever make. The second contrast is time itself. On one hand, there is the seemingly infinite time of the 13.8 billion-year-old universe, and on the other, there is our own lifespan, which is shorter than a single drop of water in the ocean. Compared to the age of the universe, an 80-year human life is less than a billionth of the blink of an eye. The 5,000 years of recorded human history is a fraction of a second on the cosmic calendar. This truth, at first, crushes a person. It drowns us in a sense of nothingness. We think that everything we do, every civilization we build, every poem we write, every love we feel, is nothing more than a speck of dust that will be blown away by the winds of cosmic time. Like the mastodons and dinosaurs, we too will one day disappear, and the universe will continue to flow on, without even noticing our existence. This is the tragic truth of existence. We are like mayflies living on the bank of a cosmic river, with only a day to live. We have too little time to fully understand where the river comes from or where it is going. Therefore, everything we do can seem temporary and meaningless. But here is the but moment. Perhaps meaning is hidden precisely in this brevity. Because, for something to be valuable, it does not have to be eternal. The beauty of a sunset comes from the fact that it lasts only a few minutes. The scent of a flower becomes more precious because we know it will wither next season. Our lives are like that too. They are so short that every moment becomes a gift, and what we accomplish in this short life becomes even more miraculous. The fact that a being with only an 80-year lifespan tries to understand a 13.8 billion-year history is as astonishing as the universe itself. We are the only known part of the universe that can think about itself, question itself, and search for the meaning of its own existence. We are the moment the universe becomes aware of itself. And this moment, no matter how short, is more valuable than eternity. You, in this fleeting life, are a miracle that exists for just a moment, and this moment is an opportunity for the universe to see with your eyes, to think with your brain. The third, and perhaps most poignant contrast is between absolute loneliness and deep connection. The distance to Andromeda taught us something. Galaxies are desolate islands separated by vast oceans of space spanning millions of light years. This is a cosmic loneliness. The Milky Way, with its 400 billion stars, is like a raft drifting alone in this dark ocean. The nearest large raft, Andromeda, is a horizon we can never reach. This feeds one of our species' fundamental fears: loneliness. Are we alone in the universe? Is there another consciousness in this vast emptiness for our voice to echo against? The distance to Andromeda seems to whisper that the answer to this question is probably yes, we are alone. Because if it is impossible to have a meaningful dialogue even with our closest neighbour, what hope can we have for those further away? This is a cold, hard feeling of loneliness that seeps into one's bones. We are the orphans of this universe. But here is the but moment. Perhaps we are not alone. Perhaps we're just looking in the wrong place. Because connection does not have to be established through radio signals or starships. The deepest connection has already been established at the atomic level. Every carbon atom, every oxygen atom that makes up your body was forged in the heart of a star billions of years ago. When that star died, it scattered these elements into space, and those elements came together to form a new solar system. a planet, and eventually, you. You are made of stardust. This is not a poem. This is a literal fact. Therefore, when you look up at the night sky, at Andromeda, you're actually looking at yourself. You're looking at a distant cousin. The atoms that make up your body and the atoms that make up a star in Andromeda came from the same cosmic furnaces. The 2.5 million light-year void between us cannot erase this fundamental connection. You're not just an observer living in this universe. You are the universe itself, a part of it that has gained consciousness, that observes itself, and that tries to understand itself. Therefore, the deep longing you feel when you look at Andromeda is perhaps just a desire to return home. These contrasts, these paradoxes, show us our place. We are at once powerful and weak, wise and ignorant, mortal and eternal, alone and connected to everything. This is the complex and contradictory beauty of being human. But there is one more contrast we will discover on this philosophical journey, perhaps the most important one. This is the fine line between hope and acceptance, because there is one more thing these distances teach us, and that lesson could change our outlook on the future, our dreams, and even our goals as humanity. Because in the face of these cosmic truths, and in the face of these cosmic truths, we confront one of humanity's oldest dilemmas, the fine line between hope and acceptance. Because the distance to Andromeda brutally kills one of science fiction's favorite dreams, the dream of interstellar travel. But, at the same time, it shows us a deeper, more attainable goal. This is the contrast between exploration and survival. On one hand, there is that endless desire to explore, coded into our species' DNA. New continents, new worlds, new stars. This desire drove us out of Africa and spread us to every corner of the planet. It took us to the moon and sent robots to Mars. Therefore, it is natural for us to look at Andromeda and see it as the next target. But, as we have seen throughout this story, this target is unreachable. The laws of physics build an insurmountable wall in between. This is the greatest tragedy for an explorer, a shoreline visible on the horizon but never to be reached. This situation can drive us to despair. We can fall into pessimism, thinking that our dream of spreading to the stars is forever trapped within the narrow confines of our own galaxy. Because this is the ultimate limit placed on the human spirit's desire for expansion. But here is the but moment. Perhaps the universe is teaching us a more important lesson. Perhaps the impossibility of infinite outward expansion is a sign for us to focus inward towards our own home. Because these distances show just how dangerous this universe is and how rare a place like ours is. A habitable planet, a stable star for billions of years, an atmosphere that supports complex life. These are extremely rare treasures in the universe. We are living on this treasure. And perhaps Andromeda's real message to us is this: stop looking outward, appreciate what you have. Perhaps our real mission is not to go to a galaxy 2.5 million light years away, but to protect this pale blue dot, this one home we have. When you understand this message, you cease to be an explorer and become a guardian. You're a consciousness that understands how fragile and how precious this planet is. And this understanding is far more powerful than any rocket that could take you to the stars. This brings us to another deep contrast: the boundlessness of our imagination versus the ruthless limits of physical reality. Science fiction has accompanied us at every stage of this story. Generation ships, wormholes, warp drives. Our culture is filled with a mythology that distance is just an engineering problem to be solved. This mythology gives us hope. It tells us a comforting tale that technology and human ingenuity can overcome any problem. And this tale is true, up to a point. We went to the moon. We sent a probe through the rings of Saturn. These achievements are triumphs of human imagination and perseverance. But the distance to Andromeda is where this tale ends. It is the moment imagination hits the wall of physics. Because a 4 billion year journey time is not a problem that can be solved with a better engine. It is a property of time itself. This is a tragic moment for the dreamer. To see that even the most audacious dreams are crushed by the indifferent mathematics of the universe. Because this reminds us that we have limits. It hits us in the face that we cannot do everything. We cannot go everywhere. But here is the but moment. Perhaps these limits are not a weakness, but a source of creativity. Because art, science, and philosophy often thrive within limits. A poet can express infinite emotions within the strict rules of a 14-line sonnet. A painter can create the illusion of three-dimensional depth on a two-dimensional canvas. Perhaps we're like that too. Perhaps being physically trapped in this galaxy makes us more creative, more profound, more meaningful beings. Because we have to tell stories about the places we cannot travel to, imagine the worlds we cannot visit, write songs for the stars we cannot reach. Perhaps these limits the universe has placed on us are the greatest source of inspiration that feeds our art, our science, and our humanity. You're a being who continues to dream despite these limits. Your mind is the only thing that can escape the prison of the physical world, and this escape is your greatest freedom. So, as we approach the end of this philosophical journey, we are left with a mixture of emotions. How do you feel after listening to this story? Or at the vastness of the universe and our smallness? Or a sadness filled with the knowledge of worlds that can never be reached? Perhaps both. Because these two emotions are two different faces of the same truth. Like that profound feeling astronauts call the overview effect. That unifying but transcendent feeling they have when they see the Earth from space. This is a liberation that comes from accepting our smallness in the face of the universe's greatness. It is to shed the small anxieties of our individual lives and reach a larger perspective that encompasses stars and galaxies and cosmic time. And there is a real beauty in this perspective. But the distance to Andromeda adds a different emotional tone to this beauty. Not awe, not wonder, more like a grief. Because this distance tells you that the magnificence is real, but it is untouchable. The universe has built cathedrals of light and then surrounded each one with uncrossable moats, millions of light years wide. It has created a universe worth exploring, and then made exploration in the galactic sense physically impossible. This is not a limitation of human technology. This is a limitation of physics. And facing this truth requires a kind of mourning, a mourning for the unreachable. Therefore, all these philosophical reflections on humanity's place in the universe bring us to a crossroads. On one hand, we have understood how big the universe is and how small we are. On the other, we have seen how great we are in our power to understand and imagine, even in this smallness. On one hand, there is the infinity of time and our transience. On the other, we have realized how precious and miraculous even that brief moment is. We have walked the fine lines between loneliness and connection, hope and acceptance, imagination and reality. We now know that the universe is a gallery of windows and we are beings who can look through those windows but never enter. This seems to be our destiny. But there is one more question we have not yet asked on this journey, perhaps the most unsettling one. What if this distance, this isolation, is not an accident? What if it is not a feature of the universe, but a purpose? Could these walls have been built not just to keep us out, but also to keep something else, so something much darker, in? Because, in the final act of this story, we will move beyond distance itself and address the deeper, more speculative question of why that distance might exist. Because Andromeda's silence may not just be the result of a great distance. Perhaps this silence is a conscious choice, and this possibility, the idea that this silence might be a conscious choice, takes us to an even deeper philosophical layer, perhaps the most intimate one. Because the questions we have asked so far have been outward-facing, the structure of the universe, our place, our destiny. But now it is time to turn the mirror of those vast distances upon ourselves. What do we do with this knowledge? How do we live under the weight of these overwhelming truths? The distance to Andromeda is not just an astronomical fact, it is a personal challenge, and this challenge confronts us once again with the most fundamental contradictions of being human. But, this time, these contradictions are more personal, more searing. The first confrontation is with the nature of knowledge itself. On one hand, there is this incredible body of knowledge we have acquired about the universe. On the other, there is the danger that this knowledge pushes us into inaction. This is the contrast between understanding and helplessness. We know that the universe is expanding at an accelerating rate and that distant galaxies are disappearing beyond the cosmological horizon, lost forever. We know that in about 100 billion years, a future civilization will see nothing but its own galaxy in the sky, that the evidence of the Big Bang will be erased. This knowledge places us in a very special, very privileged moment in history. We may be among the last generations to be able to know how big and how old the universe is. This is an incredible responsibility to record, to preserve, and to pass this knowledge on to future generations. But this knowledge also creates a tragic sense of helplessness, because we cannot change this process. We cannot resist the push of dark energy. We cannot stop the galaxies from moving away. We are like observers sitting in a slowly emptying room, watching the lights go out one by one, but unable to reach the switch. This situation can drive us to inaction, to the idea that everything is meaningless. Because, if the ultimate fate of the universe is a cold loneliness, what is the point of our efforts? But, here is the but moment. Perhaps meaning lies not in being able to change the outcome, but in being able to witness the process. Because we are the only beings aware of this cosmic drama. The universe itself is using our consciousness to tell this magnificent but tragic story, and our task is not to change the outcome, but to tell the story in the best way possible, to gather knowledge, to make sense of it, and to express it through art, science, and philosophy. A doctor may not be able to save a terminally ill patient's life, but they can alleviate their pain, provide them with a dignified end. We are like the doctors of the universe. We cannot change its ultimate fate, but we can understand its story, and with this understanding, give meaning to our own existence. You are the narrator of this cosmic story. Your existence is the universe's own memory, and this carries a greater meaning than any action. This brings us to that delicate balance between the individual and the universal. On one hand, each of us is a singular, unique consciousness. We have our own hopes, fears, memories. On the other, in the face of universal truths like the distance to Andromeda, we are all the same. This is the contrast between singularity and commonality. You are the hero of your own life. The most important things for you are your family, your friends, your passions, your dreams. These are the center of your universe, and this is true. This personal world is everything to you. But then you look at Andromeda. You think about that 2.5 million light-year distance, that 4 billion year journey time, and suddenly you realize how small, how fragile that personal world is. This is an isolating feeling, because your personal sorrows, your joys, seem to mean nothing on that vast cosmic scale. The universe does not care about your existence. This is an existential loneliness. The feeling that each of us is trapped inside our own little bubble of consciousness, and that no one can ever fully understand our world. Because your experience is yours alone. But here is the but moment. Perhaps these universal truths unite us rather than divide us. Because when you look at that pale smudge of light and feel your own smallness, you are not alone. In that moment, Plato, Galileo, Henrietta Leavitt, and millions of people around the world looked up at the sky with the same feeling. They felt the same awe, the same wonder, the same sadness. The distance to Andromeda is the same for all of us. It is a universal mirror, and when we look in that mirror, we see not just our own reflection, but the reflection of all humanity. Therefore, that overwhelming feeling of loneliness might actually be the moment of deepest connection. Because what unites us is not our common victories or our cultures, but our common fragility and our common curiosity. You're one of billions of people asking this universal question, and asking this question makes you a part of the human family. This is a connection that transcends languages, borders, and time. And finally, perhaps the most challenging contrast is between curiosity and silence. We are a species that naturally asks questions. Why are we here? Are we alone? Does the universe have a purpose? These questions have been the engine of philosophy, religion, and science for thousands of years, and science has provided incredible answers to some of these questions. We have learned the age or size and structure of the universe, but to our deepest, most fundamental questions, the universe responds with a stubborn silence. This is the contrast between the quest and the lack of an answer. This is the contradiction at the heart of the Fermi paradox. There are hundreds of billions of galaxies in the universe, each with hundreds of billions of stars. Statistically, it seems almost certain that other intelligent life forms should exist. So, where is everybody? Why is there that deafening silence? The distance to Andromeda can only explain a part of this silence. Perhaps civilizations exist, but the distances between us are so great that we're unaware of each other. This is a tragic but understandable situation. But what if this is not the reason for the silence? What if the universe is truly empty? Or worse, full, but everyone is hiding? This is the greatest disappointment for human curiosity. We ask the most important questions, but there is no one to answer. It's like putting a message in a bottle and throwing it into the ocean. But knowing that the ocean is infinite and the bottle will never wash ashore. But here is the but moment. Perhaps the absence of answers is the greatest gift. Because if we knew all the answers, the quest would end, curiosity would die, art, philosophy, and science would lose their meaning. Perhaps what makes us human is not finding the answers, but asking the questions. Perhaps the journey itself is more important than the destination. This silence gives us the freedom to create our own answers. If the universe does not give us a purpose, we can create our own purpose. If the universe does not offer us a meaning, we can build our own meaning. This is the greatest creative act. You are a being singing your own song in the midst of this silence, and writing the lyrics to that song is entirely up to you. Thus, we have navigated the deeper layers of knowledge's helplessness, singularity's commonality, and curiosity's silence. These thoughts show that the distance to Andromeda is not just a number, but a philosophical prism that shapes who we are and how we will live in this universe. But there is one last angle we can view this from. This is the relationship between the past and the future. Because Andromeda's journey towards us is not just a harbinger of a future collision, but also says something about the most fundamental nature of the universe, about the arrow of time and the ultimate fate of everything. And this final thought will bring us back to the simple observation at the very beginning of this story, to that pale smudge of light. But this time, we will look at it with completely different eyes, because we will no longer see just a galaxy, we will see a reflection of our own future, our state billions of years from now. And this reflection, Andromeda's journey towards us, brings us to the final and most profound contrast of this story. This is the eternal dance between change and permanence. On one hand, there is the fact that the universe is in constant change. Stars are born, live, and die. Galaxies collide and merge. The universe itself expands and cools. Nothing stays the same. Our existence is a momentary flash in this vast cosmic flow. On the other hand, there is our desire to search for things that are permanent, unchanging, even in the midst of this change. Things like meaning, purpose, love. We are like sailors searching for a stable rock in a stormy sea. Andromeda's approach towards us is one of the most concrete examples of this change. Billions of years from now, our night sky will be unrecognizable. The two galaxies will merge to form one giant elliptical galaxy called Andromeda. This may seem like a tragic loss. Our beautiful spiral galaxy, with its elegant arms, will be lost within an older, redder, and more boring galaxy. This might feel like the end of the universe as we know it. Because that familiar landscape, that Milky Way arch, will be just a history book memory for our descendants' descendants'. But here is the but moment. Perhaps this is not an end, but a beginning. Because this merger will trigger a new and massive wave of star formation. When the gas and dust clouds of the two galaxies collide, trillions of new stars, trillions of new solar systems will be born. This is not a death, but a rebirth. The universe builds new structures by tearing down old ones. This is the most fundamental cycle of nature, and and we are a part of this cycle. Therefore, Andromeda's approach teaches us that change is an inevitable but also a creative force. Instead of fearing change, we can embrace it, because just every end carries the seed of a new beginning. You are a being standing in the midst of this change. The changes in your own life are a small reflection of those great cosmic changes, and just like galaxies, you too have the potential to be reborn after every change. This brings us to perhaps the most personal contrast of this story: fear and curiosity. The distance to Andromeda and all the truths it contains are kept, at first, frightening. The fear of loneliness, the fear of meaninglessness, the fear of smallness. Facing the fact that we are a speck of dust in this vast, indifferent universe sends a shiver down one's spine. This is what H.P. Lovecraft called cosmic horror, the moment of realizing how insignificant and how fragile humanity's place in the universe is. This fear can paralyze us. It can push us to flee from these truths, to ignore them, and to retreat into our own small, safe worlds. Because living with these truths is hard, it can lead to sleepless nights, to existential crises. Therefore, many people avoid thinking about these topics. This is an understandable defense mechanism. But here is the but moment. Perhaps the antidote to fear is curiosity itself, because what has brought this story to this point is not fear, but curiosity. The curiosity that led al-Rahman al-Sufi to record that small cloud, the curiosity that led Charles Messier to catalogue it, the curiosity that led Henrietta Leavitt and Edwin Hubble to solve its secret. Curiosity is a force that pushes us towards the darkness. It makes us try to understand the unknown instead of fearing it. And when we understand, fear often gives way to admiration, to awe. The distance to Andromeda may be frightening, but the elegance of the methods we use to measure that distance is awe-inspiring. The emptiness of the universe may be unsettling, but the beauty of the galaxies floating in that emptiness is breathtaking. You are a being who harbors both of these emotions. You can be both afraid and curious. But the choice is yours. Will you let fear paralyze you, or will you let curiosity carry you forward? This story is proof of how powerful and how transformative choosing curiosity can be. And so, at the end of this philosophical journey, we return to where we began, a clear autumn night, that pale, silvery smudge in the sky. But we no longer look at it with the same eyes. We no longer see just a distant galaxy. We now see the triumph of the human mind, the paradox of knowledge and impotence, the meaning within the brevity of time, the deep connection within loneliness, the balance between the desire to explore and the responsibility to protect home, the dance of imagination and reality, the creative power of change, and the victory of curiosity over fear. All these contrasts are folded into that single speck of light. Andromeda is no longer just an astronomical object. It has become a mirror for us, a mirror that reflects our own deepest fears, our greatest hopes, and our most complex contradictions. When we look at it, we solve not a secret of the universe, but a secret of ourselves, and this, perhaps, is the greatest reward of this entire journey. Because, when we try to understand the universe, we're actually trying to understand ourselves. You have the privilege of looking into this mirror, and what you see in that mirror can change you forever. We have now come to the end of our journey. We have passed through the crushing weight of numbers, the dizzying speed of discovery, and the calm depths of philosophy. We have seen that the distance to Andromeda is not just a distance, but also a boundary, a lesson, a mirror. This journey has shown us that the universe can be both brutally indifferent and unimaginably beautiful. It has reminded us both how insignificant we are and how miraculous we are. It has confronted us with the impossibility of our greatest dreams, but it has also guided us to find deeper and more attainable meanings. At the end of this story, we are perhaps left with more questions than answers. But maybe that's a good thing, because questions are what keep us alive, what move us forward. Now, it is time to take all this knowledge, all these emotions, and gather them one last time to understand the ultimate lesson this terrible but magnificent distance leaves us with. Because Andromeda has one last story to tell us. And this story is about how it all began and how it will all end. In this journey, we have seen how terrifying distances can be. But I have not told you the greatest secret of the universe. In the first moment of our existence, space itself expanded billions of times faster than the speed of light. It transformed from a point smaller than an atom into a vast cosmos in an instant. In our next journey, we will explore this incredible moment of cosmic inflation. Are you ready to go to the beginning of time?